Think about temperature for a moment. How hot can things get? There's no limit, right? Keep adding energy and things get hotter and hotter. The sun's core reaches millions of degrees. Some stars burn at billions. There's no maximum temperature, no ceiling. So what about cold? How cold can things get? You might think the same logic applies. No limit going down, just like there's no limit going up. Colder and colder and colder, forever. Wrong. There's a bottom, an absolute limit, a temperature you cannot go below, no matter what you do. We call it absolute zero, minus 273.15 degrees Celsius, minus 459.67 Fahrenheit, or just zero on the Kelvin scale. But why? Why is there a coldest possible temperature when there's no hottest? What makes cold different from hot? And what actually happens at absolute zero? Does everything just stop? The answer reveals something profound about what temperature really is. And once you understand it, the existence of absolute zero isn't just obvious, it's inevitable. First, forget what you think temperature is. It's not how hot something feels. That's subjective, useless for physics. Temperature is about motion, atomic motion, molecular motion. Everything around you, this screen, the air, your hand, is made of atoms, trillions of them. And those atoms are moving, vibrating, jiggling, bouncing around constantly. In a solid, atoms vibrate in place. They're locked in a crystal structure, but they're shaking, faster when hot, slower when cold. In a liquid, atoms slide past each other, still moving, still jiggling, but now they can flow. In a gas, atoms fly around freely, colliding with each other, bouncing off the walls of their container. This is air. Nitrogen and oxygen molecules zipping around at hundreds of meters per second, right now, in this room. And here's the key point. Temperature is a measure of this motion, specifically the average kinetic energy of the particles. Hot means fast-moving atoms. Cold means slow-moving atoms. That's it. That's what temperature is. When you heat something, you're adding energy, making the atoms move faster. When you cool something, you're removing energy, making the atoms move slower. Simple. Now you see the problem. How cold can you make something? You remove energy, the atoms slow down. Remove more energy, they slow down more. But there's a limit to how slow they can go. Zero. Atoms can't move slower than not moving at all. They can't have negative speed. Motion has a minimum. Stop. Zero velocity. And since temperature measures the average kinetic energy of atomic motion, there's a minimum temperature. The temperature where atomic motion reaches its minimum possible value. That's absolute zero. It's not some arbitrary number. It's not a practical limitation of our refrigeration technology. It's a fundamental limit built into the nature of motion itself. You can't go below zero speed. Therefore, you can't go below zero temperature. That's it. That's the answer. Motion has a minimum, so temperature has a minimum. Here's where it gets interesting. I just said atoms stop moving at absolute zero. That's almost true, but not quite. And the reason reveals something even deeper about reality: quantum mechanics. In classical physics, Newton's world, you could imagine atoms sitting perfectly still. Zero motion, zero energy, just frozen in place. But quantum mechanics says no. There's a principle called the Heisenberg uncertainty principle. It says you cannot simultaneously know both the exact position and the exact momentum of a particle. If an atom were perfectly still, zero velocity, zero momentum, you'd know its momentum exactly, zero. And if it's sitting in one spot, you'd know its position exactly too. That violates the uncertainty principle. Nature doesn't allow it. So even at absolute zero, atoms can't be completely motionless. They must have some minimum amount of motion, some irreducible jiggling. We call this zero-point energy. It's the lowest possible energy state, but it's not zero energy. It's the minimum allowed by quantum mechanics. This is why helium, liquid helium, never freezes solid at normal pressure, even at absolute zero. The zero-point motion is too large. The atoms jiggle too much to lock into a crystal. They remain liquid, quantum liquid. Even at the coldest possible temperature, motion never completely stops. So what happens as you approach absolute zero? Strange things, beautiful things, things that reveal the quantum nature of reality. First, gases condense into liquids. Then liquids freeze into solids, normal enough. But if you keep going, cooling a gas down to a few millionths of a degree above absolute zero, something bizarre happens. The gas becomes a Bose-Einstein condensate. At normal temperatures, gas atoms fly around independently, each doing its own thing, moving in different directions, at different speeds, a chaotic mess. But near absolute zero, something incredible happens. The atoms slow down so much that their quantum wave functions start to overlap. And when that happens, they stop behaving as individuals. They become one, a single quantum entity. Thousands or millions of atoms acting as a single coherent quantum object. It's like a room full of people dancing randomly, suddenly synchronizing into a single choreographed movement, all moving together, all doing exactly the same thing. This is a new state of matter, not solid, liquid, or gas, something else, a macroscopic quantum state, large enough to see with your eyes, but behaving according to quantum rules. Think about that. Quantum mechanics usually governs tiny things, electrons, photons, individual atoms. But here, you can see it, a blob of matter the size of a grain of sand, behaving as one quantum object. And it does strange things. Superfluidity appears. Liquid helium becomes a superfluid below about 2 Kelvin. It flows without friction, without viscosity. It can climb up the walls of its container and flow out. It can flow through holes so small that normal liquids can't pass through. Why? Because friction requires energy dissipation, requires atoms bumping into each other and losing energy. But a superfluid is a single quantum state. There's no mechanism for energy loss, no friction. The liquid flows perfectly, forever. Put it in a container, spin it, the liquid keeps spinning forever. No slowing down, no stopping, because there's nothing to slow it down. Superconductivity appears. Certain metals, when cooled below a critical temperature, lose all electrical resistance. Current flows forever without losing energy, without generating heat. Send a current through a superconducting loop. It circulates forever, years, decades, with no power source, no battery, just flowing, because there's no resistance to dissipate the energy. Again, quantum mechanics. Electrons pair up and form a coherent quantum state. They flow together as one, no scattering, no resistance. These aren't small effects. They're macroscopic quantum phenomena, visible demonstrations that quantum mechanics isn't just about tiny particles. It governs the behavior of matter at the coldest temperatures. Here's another strange fact. You can get close to absolute zero, very close. Scientists have cooled atoms to billionths of a degree above zero. Nano-Kelvin, almost there. But you can never actually reach it. Why not? thermodynamics, the third law specifically. Cooling something requires removing energy. And to remove energy, you need something colder to absorb it, a heat sink. But if you're already at the coldest possible temperature, there's nowhere for the energy to go. No colder reservoir exists. You can't remove that last bit of energy. Every cooling method gets you closer, but each step requires more effort, more energy, more time. And the closer you get to absolute zero, the harder it becomes to go further. It's asymptotic. You approach it, get arbitrarily close, but never quite reach it. This isn't a technological limitation. We're not just waiting for better refrigerators. It's fundamental, built into the laws of thermodynamics. Nature won't let you reach absolute zero. Not because it's difficult, because it's impossible. So why does absolute zero exist while no maximum temperature does? Because temperature measures motion, and motion has a natural zero point. You can't move slower than not moving, but there's no upper limit to motion. You can always move faster, add more energy, higher temperature. The sun is millions of degrees. Supernovas are billions. Particle colliders create temperatures trillions of degrees above the sun's core. No limit upward, but a hard limit downward. Well, actually, there might be a maximum temperature, the Planck temperature, about 10 to the power of 32 Kelvin. Above this, our current physics breaks down. Space and time themselves become uncertain. Quantum gravity takes over. But that's a different kind of limit, a limit of our theories, not necessarily of nature. Absolute zero is different. It's real, fundamental, unavoidable. And the closer you get to it, the more quantum mechanics takes over, the more the classical picture of bouncing balls fails, the more you see the true quantum nature of matter. Hot things behave classically, atoms bouncing around like tiny billiard balls, predictable, understandable. Cold things behave quantum mechanically, wave functions overlap, particles act collectively, friction disappears, resistance vanishes. And at the coldest possible temperature, quantum effects dominate completely. Particles don't just slow down at absolute zero. They reveal what they really are, not little balls, not tiny planets, but quantum objects, wave-like, probability distributions, entities that can occupy the same state, that can act collectively as one. That's why nothing can be colder than absolute zero. Not because we can't build better refrigerators, but because cold means slow atomic motion, and motion has a minimum, zero. And quantum mechanics adds a tiny bit of irreducible jiggling on top. It's not arbitrary. It's not a limitation of technology. It's a consequence of what temperature really is, a measure of motion. And motion has a bottom. When you understand that, absolute zero isn't mysterious. It's inevitable, beautiful, and deeply connected to the quantum nature of reality itself.